Thank you for having me. Especially thank you to Mickey, to all the organizers, and to Amazon for having us here. Like, I know running events in Australia, finding the space, someone to put us on, someone to put us up is the hardest thing. So I really appreciate it. All right, let's crack on. What are we going to talk about today? So before I begin, this document is online, bit.ly GCIL 2020. So the document that you read is the document that I'm working from. When I originally pitched this workshop, I said, half a day, 3 hours, something like that. In all the times I've given this workshop, I've never been able to keep to that time. So we're not going to get through everything on here. There's some 40,000 words in this document. So I'm just going to touch on the interesting things. You can read the rest yourself. I think that's the easy way. I will also talk a little bit slower, a little bit louder. Where this workshop came from needs a bit of explanation. A couple of years ago, I wrote this tweet. It said, 3 rules for dating my code base. Here are the 3 rules for, if you want to come and work with me and write good code, which is a little bit presumptuous. But also tweets being what they were, you could only fit 3 tiny suggestions in a tweet. And so the next day I had 3 more ideas. And I thought, this could go on and on and on. I think there are some ways that we can talk about writing good Go code and come up with a list of suggestions. And also at the same time, I'd been approached by O'Reilly to do a book about Go. And I started working on that, and then it kind of fell apart for 2 reasons. One is that I would be doing all the work, and their document preparation system was very inflexible. If I'm doing all the work, I want to have control all the way through to when it comes out as a book, and that didn't seem to be a thing that they were able to do. And the other thing is just the number of hours it takes to write a book. And the problem with that is that either you find all this time, 300-400 hours of time, and if you fall short, well, then there's no book. So there's no partial credit. And that kind of struck me think of the way that we write software. We would try very hard not to say, right, we're going to sit and write for 2 years and then come up with the program at the end. That's a very risky way of developing software, and it kind of felt a really risky way of writing a book. So what I began thinking about is, how can I take these ideas that I had and present them in a way that that I could stop at any time, if I ran out of time or if just didn't have as much to talk about as I thought. And so this is the result. This workshop, the articles that I write on my blog, the conference talks that I give are all kind of aspects of that. It's a way of trying to write a book in an agile fashion. So, in fact, all this material here is actually all the stuff that I've written in this book. It comes from the same source. So this is the best version of the ideas that I know how to present. As I said, this is where this version of the document is. So you can read along if you like. It's also Creative Commons non-commercial share alike. So basically, you can do anything with you want, but except turn it into your own book and sell it. That's all. But please take these ideas, pull them apart, critique them, riff on them. If they inspire your own ideas, it's all good. Okay. So one other thing before we get into some of the points I want to talk about is, the more that I have been thinking about software development, I've been involved in Go for 2010 is when I started. I've been through a bunch of companies who've been from writing Go at very early stages when things were very, very primitive in the language. We didn't have a lot of tooling, up to companies that are now established. It's not that you come in as the one Go programmer or the programmer who wants to change the company to use Go. Now, it's an established thing. Like you say, well, what languages are we using? Oh, we're using some Node.js, and we're using some Java over here, and we're using some Go for these bits. But the thing that I want to stress is that I don't believe, like these are my opinions. They are not the truth and they are not facts. They are fundamentally my opinions. They're informed by what I've seen using Go over the last decade and the reading that I've done. But the thing that I want to point out, there's a story here, you can read it yourself, is that these are my opinions and the suggestions I have formed from my experience. I present them to you as like, I think these are ideas that work, but I also open you to challenge me on them, to question the basis that I believe a certain thing or I'm recommending a certain thing. Given the time that we have, it may be a very short challenge, or we can talk about it later, but again, these are just my ideas. Take them, incorporate them into your own set of engineering beliefs. Because all of the things that I've been thinking about, I've tried to summarize Go and like how to write Go code in a bunch of different ways. We use words like simple and readable and clarity and productivity, but ultimately what I've come to believe is that these are all synonyms for one word, maintainable. That's the only thing that matters. Like how you get there is important, but the goal has got to be to write maintainable software. Because if people can't maintain the software that you write, if you can't join a team and help other people continue the software they've written, well, there's no point. Like the whole goal is to make maintainable software. And so if there's one guiding idea that encompasses all the other things I'm going to present today, it is the fundamental goal is to be maintainable. So I've tried to put these ideas into groups. And that has honestly been one of the most challenging things of saying, does this fit in this group or that group? So this is a loose grouping, but what we're going to start today is with declarations, because the declarations are kind of the fundamental of any programming language. Like they're the names that we use to talk about our identifiers, our symbols, the name of our functions, our packages, everything has a name. And so the naming is critical to writing good software. And it's, I think, even more important inside Go because we have so few other concepts to really talk about. Like it's a very straightforward, simple language. We only have 25 keywords. There isn't a lot of different ways that we can say things. And so the names that we choose in our program are of outsized importance. So to start with one idea, choose identifiers for clarity, not for brevity. And to go back to what I opened with, I'm trying to avoid absolute statements like you must or you should never. I'll say things like should or prefer or avoid. But I'm never saying you must do or must not, because those absolutes don't exist. There are always exceptions to the rule. There are always choices that we make. And this is part of design. Software design is the act of making these choices and these trade-offs and saying, I choose this over that because reasons. So, as I say, we don't optimize for clever one-liners. Go isn't a language where we try to write one line where three would do. It's just not in the spirit of the language. Like we don't optimize for the size of the code on disk. Like we don't try and have the shortest program. And we don't really try to optimize for trying to have the shortest program to type into a computer either. We are looking for clarity, not brevity. Yes?
How does it go as though that a lot of times you see a lot of very short writing? The canonical example is the export handler with R and W.
Yeah. So the question is about variable names. I'm going to hold that for going right up. So anything in Go that is an identifier has a name. Like we can name all these things: types, structures, interfaces, functions, methods, packages, constants, your variables, your formal parameters, and the return values. This is all the things that we can declare. Naming is key to readability. So the names that we choose are critical to our program. If we choose names poorly, they contribute to a program that's harder to understand. So naming is important. And just to come back to your question, most of the stylistic elements of a Go program are defined by Go format. It pretty much restricts how we can lay out lines on a page, where we break the line, what we put into a block, where the semicolons, where the braces go, things like that. So inside that framework, we can make statements like this. We can say, the greater the distance between a declaration and the last time it's used should have an impact on the more descriptive the name. And similarly, the more frequently the name is used in a particular place, maybe it can be shorter. Because if you're saying something over and over again, generally in any language you tend to abbreviate it, you tend to find a shorter way to say the same thing. And these two observations interlock. For example, the names of local variables, I said should, probably can be shorter than the names of formal parameters. So when we're talking about a name, we should say things like, a good name is concise. It's not the shortest it can possibly be, like that is just one character, but it shouldn't waste space on things which are extraneous. And I have some examples coming up. I say that a good name should have a high signal to noise ratio. Like every character in that identifier should pay for itself. It shouldn't just be there because of some other reason. It should take part in identifying what this identifier does. A name should describe what the thing does. It should describe the application of a variable or a constant. It shouldn't describe what's inside it. That's an important distinction. It should describe the result of a function or a behavior or method, not how it does the thing. So if you're talking about a method, the name of that method should be what it does, not how it does it. Similarly for packages, which we'll talk about later, the name of a package should describe what this package is going to do for you, not how it does it, what's inside it. And that's probably fairly common sense, but the one that I think is a little bit novel is that a name should be predictable. When you see a name, you should be able to know from that name what that thing does through convention. The word taxi is almost universal in every city that I've been to. Like when you say taxi, you get a car that's going to drive you someplace. We know taxi, we know bus, we know those words, we know what they do. So let's talk about this in more detail. To speak directly to your question, I believe that the larger an identifier scope, like the longer it lives, the larger its name should be. Rob, in his usual cryptic way, has said we don't want short variable names or long variable names, we want variables of the right length. And so how are we going to decide what right is? Andrew Duran suggests the greater the distance between the declaration and the use, the longer its name should be. Kind of saying the same thing. So now we can draw some guidelines. Short variable names work well when the distance between the declaration and the last use is short. So short functions could have short identifiers. Well, long variable names need to justify themselves. The longer they are, the more value that needs to be provided. If you're going to have a 20-character name, it's got to have 20 characters of value in there, not 5 and some suffix. For similar reasons, don't put unnecessary things in the names of your variable. Don't, for example, put the name of the type in the name of the variable. It's not really telling you anything. It's just wasting space. It's making it longer without being more descriptive. We'll gloss over these and come to some examples. Let's look at an example. Examples are always fun. So we have a type called person. It's got a name and an age. And we have a function that is going to take the average age of a list of people. First of all, we have to deal with the case at the top, which is if we have no people, then we have to return some value because we can't divide by 0. Then we loop over the people. We sum up all their age, keep a count, and then return just the average of that. So in this example, the range variable p is declared here and only used one line later. It's only referenced once, only used once. We could have called it person, but like it doesn't live for as long as that. It's in some ways a temporary variable. Like it's only used here to hold the induction value and then to grab the age. So for myself as the reader to understand what p does, what its use in this function, well, I only have to read these 2 lines. By comparison, like people, which is the one of the formal parameters, lives for most of the length of the function. So what do I say here? It's live for the whole body. It's referenced 3 times over 7 lines. The same is true for sum and count. And so the reader has to, so that is in some ways justification for the line, for the name being longer. The reader has to scan a wider number of lines to locate them, so we give them more distinctive names. If they were just S for sum and C for count, or maybe N or something like that, yeah, we would have had, these would have all been short variables, but we would have mixed their importance. So P is not particularly important. It's just the way that we're accessing the age as we go around the loop. But the count and the sum are much more important because we actually use them to compute the result. So by choosing different length identifiers, I signal to the reader that these are probably more, that these ones are probably more important than that. Okay, so those are, that's kind of the basic theory. Like it's never you should make all your variables short or you should make all your variables long. It is use them as a tool to emphasize to the reader what are the important parts and what are the kind of transient parts. But of course, this advice is always contextual. There is always a but or a what if. So we have these 2 loops. What's the difference between calling it I or calling it index? I mean, is this form fundamentally more readable than that? I'd like to argue this is just as good as that, and perhaps more because of familiarity, which I'll come to in a second. I is just used for the loop induction variable. It's just a counter. It's just there because we need to count things. Calling it index just to make things, just because, doesn't really add anything to the function. And as a note, if you find yourself with so many nested loops, one inside another, you run out of i's and j's and k's, then that's a symptom not that you should have longer names for induction variables, that maybe you should break the function up. But to come back to talking about things being contextual, here's an example. I don't know if any of you have dealt with network switches, but in SNMP there is this notion of this thing called object ID. It's the phone number, the identifier for a particular piece of information that a switch has. And so calling the field OID, it's nice and short already, like it's already a acronym. And it's important because everybody who works in SNMP knows what OID is. Like it's in the documentation, it's in the words that they use all the time. If we made it O, then every time the reader who's living in the network land reads this they're going to have to translate O means OID, which is object ID. So in this case, we choose to use a slightly longer variable name because of the familiarity. Everyone knows that we're talking about an OID. That's its name. An interesting note is that because I chose to retain OID, the other parameters should probably be, for consistency, should probably be the same length. Like, don't mix, as I say, don't mix long and short formal parameters in general. Another property that I think of a good name is that it should be predictable. And this goes back to like not the short name or the long name, but a predictable name. For example, when you're talking about a database handle, if sometimes it's called SQLDB or just D or DBase or capital DB or sometimes database, depending on where it appears in the code, that's really confusing for the reader. They have to remember these 5 different things are actually the same thing. It's just whoever wrote the code decided to call it DBase today, and then someone else came along and in another part of the code they called it database, or they wanted to use D because some other identifier had been taken. So this has got nothing to do with the length of the identifier, but the fact that it changes throughout the program. Like there's no commonality and there's no predictability. If instead the author had chosen, anytime we talk about a type of SQLDB, we're going to call it DB. We're going to call it DB in the formal parameters, in the return values, in a local declaration, in a receiver. And so that would mean every time you saw a DB, you didn't even need to think about its type. Oh, that's the database thing. And the similar advice applies to method receivers. Like in Go, we generally don't say this or self. The name of the receiver is generally some contraction of its type. So if it's a reader type, we just call it R. And the advice there is, if you have a bunch of different methods, make sure the receiver is always the same. You don't call it one thing for one method and another thing for another method, because that is more confusing. But just to finish this discussion, when we're talking about predictability and commonality and kind of tradition, there are lots of traditions that we have in software development. I, J, and K are loop induction variables. This actually comes from Fortran because, does anyone know the story about Fortran? Okay. I is the first letter in the word integer. And I believe that all variables in Fortran that start between I and N are integer variables because they were the first couple of letters in the word int. Anything else, like A, B, C, D, E, are floating points. I think that there's a footnote there that explains it. Similarly, N, like just generally when we're counting or accumulating things, N is very common to use as the name for that accumulator or that counter. N things. I want the nth element of an array. V is common shorthand for a value for like a generic encoding function. Like if you look at the encoding JSON packages or anything that takes a structure and turns that into some bytes, or takes some bytes and turns it back into a structure, generally they call that parameter V, just for the value, the generic value. A and B are very commonly you see for 2 parameters of the same type for some comparison. So you'll see them in the sort function. Sort.less takes the parameters called A and B, because we know nothing about them really other than they're the same type and we're comparing some property of them. So we can't give them a more descriptive name. We know very little about them. X and Y, similar. We can't call our strings string because string is actually a pre-declared type. That would be very confusing. So S is when you just have a string that you're building, S is the commonality. And these are things that we all hopefully internalize as Go programmers, that when we see a function that ends with printf, we know it takes a formatting flag. That's just convention. The difference between println and printf is that printf takes some format string. Functions that begin with write, generally generally write out, take a string and turn it into bytes. Things like that. So this comes back to what the programmer expects, what the reader expects. With the same as the DB example, when you see an I, just somewhere in a piece of code that's just flashed up on the screen, you are, I argue, likely to say I is probably some kind of loop induction or a counter or something like that. It's very rare for I to be used for anything other than looping. And one case I could think of that would happen is when if you found a piece of code where someone started all their variables at A, then B, then C, then D, and you just ended up with I because that was the next one. So this is all about just follow convention because that helps build a shared understanding. Moving on. I believe that a variable's name should describe its contents. And that means you should avoid putting things like its type in the name. An example I have there is that, like, if you think of the names of your pets, the name of the pet, like my dog's name is Frank. It's not Frank Dog. I know it's a dog. Like, it's very obviously a dog. And this seems like a silly example, but from the compiler's point of view, it knows it's a map. You told it. Like, it understands it's a map. You don't need to constantly repeat to the compiler, the map is a map. So we've talked about things which are not great about this declaration. So it's kind of redundant to call it a map. Like, the compiler knows that users is a map of strings to user. But to kind of drive home, okay, let me actually ask it this way. Who thinks it, would anybody like to argue for this style? Do you think it's actually okay? Yes. Go ahead.
Yeah, so because you can arrange the user struct in all sorts of like included in an array. So for other developers to maintain it, they need to know how to access the information.
Yeah. Okay. Let me come back. I try to make a slightly bigger argument. Yeah.
I think this comes a lot from people who work with untyped languages, where they don't have type information in the variables and you just stick it there.
Let me just finish the point, and I'll come back to both of you. Like this is one of the things that works for me, but as again, I'm just presenting my opinions. I don't claim to have the truth. So let's consider that we continue this pattern. We have a map of users from strings to users, and we also have some companies, and we have some products. And so following the pattern, they become users map and product map and companies map. And they all map to different types. So you can't mix and match them. You can't accidentally put a company's map where expecting a product map, because the compiler already fixes that. So in some ways, the suffix that it's a map isn't actually helping the compiler. Maybe it's helping you as the reader. Then if you're dealing with the case where you have a map of users and perhaps a slice of users if you're doing some kind of manipulation, yes. But look at what happens if we just take off the map. Now we have users. It's a map of strings to user. Companies, string to company, products. And one thing I want to point out, it's plural, because if we went from user map to user, that's a singular. We would have a map talking about a singular. So even if we can't agree on the suffix, you should definitely, I think it should be pluralized. And the kind of point I'm trying to make here is, if users isn't descriptive enough, then calling it users map isn't going to help. I agree with you, this is contextual. If you have a kind of transformation function where you're working from a map of elements to a slice of them or some other transformation, maybe to make it easier, you do want to call out the source and the target. Actually, I think I have an example of that. Yeah, let me try my next example and see if I can convince you there. So my suggestion to avoid a suffix that the suffix that resembles the type of the variable. And I want to try and apply this advice to function parameters as well. For example, this is a made-up example. We have some kind of configuration structure. We pass it into something that knows how to write it out. I argue that calling it lowercase config and uppercase config is kind of redundant for the same reason that I argue users map is redundant. In this example, maybe conf would do. Maybe C would do if the lifetime of that thing is very short. Like if this is doing maybe one transformation, then passing it on. So the name of the variable is not important, its contents are. So maybe. The case I want to make, which might be applicable to your point, is this one. Consider what happens if we have two config values. Maybe the purpose of the function we're writing is to transform from the old to the new. Calling them conf1 and conf2, I think is problematic, because the only difference between conf1 and conf2 is the last character on the end. Calling them config1 and config2 is no better. The only difference between them, they have the same type, so you could accidentally transpose them from just a 1 to a 2. So the argument I'm trying to make is when you are doing something that transposes a configuration from an old to a new. Say you take a configuration, you apply some behavior over the top, and you return a new one. Don't call it conf1 and conf2. Call it like original and updated. Like make it super clear. Like call it source and target, whatever you want. Make it very, very clear, so that it's not just the suffix on the end. This number 1 or number 2. It's the totally different name. Yes.
In the case of this, what I sometimes struggle with is actually finding an expressive name describing what I'm mapping from to. I mean, it's like either user by ID, user by name. These types are kind of more complex mappings between two types. You want to kind of be able to express somehow with the name of the variable.
Yeah. So the question is, well, okay, if we need a descriptive name, sometimes that name is hard to come by, and sometimes they do end up being quite verbose. Let me show you some examples from the project that I work on. This comes up for me a lot when writing. So writing these kind of sort type functions. It's like cluster by name, or there's actually a more complicated one that sorts virtual host by name and then by route within the name. I think it might even be called something like virtual host by name and route, or something like that. Sometimes you have to be call this one longest route first, because that's what it does. Virtual host by name. So sometimes that helps. And the reason why being quite a long name is then you end up with something like this. Sort.stable, virtual host by name, and the slice you pass in. So in trying to help out the reader, like breaking most of the rules, like I said, don't talk about the type and the name, but in this one case, makes it pretty reasonable. Where given the interface of sort.sort, the compiler isn't going to help you. Any sort interface will fit through that hole. So you should use the name. One thing I want to talk about, and this doesn't come up all the time, but don't let package names steal the names of good variables. We have the famous context.context package, which means that we can't call the parameter context anymore. Just won't compile. This is why you always see it written as ctxt, context.context. And the global zeitgeist of Go developers has learnt that CTX in the first parameter is always a context. There's another, I haven't linked it here, but there's another example the reason the database package is called database/SQL is database is a really good variable name for your database connection. So I can probably find the discussion where, and it's probably actually that it's the name of the package was never db/SQL, because again, db is a great local variable for your database. So that in the design of those packages, when they added them to Go1, they put some thought into how is the caller going to use this? Are we stealing a really good local name for the package? Okay. So the next thing I want to talk about, I think there's like 1 or 2 sections here, then we'll take a little break, is declaration style. That is, in Go, we have so many ways of declaring a variable. Here's 6. X colon equals 1, Y 2, this kind of more fully specified version. We could do it on 2 lines or 2 statements, declare it and then initialize it. We can put the type on the right-hand side rather than the left-hand side. And we can kind of combine all 3 of them together to have this form. And that's just for variable declarations. This list doesn't include receivers, formal parameters, name return values. There's probably a few more that I haven't thought about. And this is something that I think is a point of concern for developers coming to Go. It's slightly difficult for me to kind of put myself in their shoes, because when I was coming up in Go, the canonical Go style was basically what Rob Pike and Andrew Durand wrote. We just felt like there was so little Go code out there. It was mainly the standard library. We read the standard library and internalized that. But we internalized it just because that was the only Go code there. There's never been a strong justification for which form to use. And so, given that I can find 6 different ways to initialize a variable, plus all the others, that may have an impact on readability. That may have an impact on, like, why is someone using this strange form of initialization? Like the simplest things, like initializing a variable, we have so many different ways to do it. That can be inconsistent. As I said, Rob has said on a few occasions that this is probably a mistake, that there are too many ways to declare a variable, but it's kind of too late, a little bit too late to change that now. So what I want to present to you is the way that I try and make sense of all these different options. And that is, I try and boil it down to 2 different forms. So for example, when declaring but not initializing, so we want it to be the default value, the 0 value for the type, use var. That's the form that I use. So players is an int, it gets 0 by default initialization. Things is a nil slice of thing, and this is an empty thing. And the justification I want to give to you is that the use of var here acts as a clue to say the variable has been deliberately declared as the 0 value. We're deliberately letting it fall to the 0 value. And I try to only use this form when I actually want that behavior. Like if I declare a Boolean, I don't initialize it to false, I just let it fall to false, for example. And there's some support, I can find some supporting evidence that this is consistent with the way you declare variables at the package level. You can't use the colon equals syntax at the package level. You have to use var. But I'm going to make a case against package level variables later on. So let's look at the opposite. When we want to declare something and initialize it, so we don't want it to fall to its 0 value, use colon equals. And I say, do this because the lack of the var prefix is a signal that we were explicitly initializing it. We're giving it a value. We're not just letting it fall to whatever its default may be. There are 2 things that kind of fall out of this. One is that this is, by default, usually the most common form you'll see there. So like by arranging your programs so that you don't declare a bunch of variables at the top and then initialize them later, by doing your initialization and your declaration and initialization close where they're closely used, this becomes the predominant form. And so instead of 6 or so different ways of declaring a variable, hopefully, even though we can't change language to remove the different syntaxes, things just naturally coalesce onto one form. And that makes it easier for the reader. Let's work through some example to kind of give a bit more justification for this. So this is the previous version, and all I've done is, using the var syntax, explicitly initialize it to the value it was going to get anyway. So give players an integer explicitly 0. Assign nil to this slice of thing, and make a new pointer to a thing and assign it. So that's kind of trying to make consistency in the other way. Say instead of preparing the short declaration form, always use var everywhere we can. And this is an example of what happens if we try and do it that way. So the first observation we can make is that the int here is very, very redundant. Like the default type for an integer constant is int, so that int is redundant. We don't need it anymore. And the same for thing. Like the type of the thing on the left-hand side of any assignment in Go is the type of the thing on the right-hand side. There's no type coercion. All the things on the right-hand side have to be of the same type, and then that expression, the result of that expression, is the type of the thing on the left-hand side. So without doing anything, like we're retaining that syntax, we've removed the extraneous bit. Like it would be less common for you to write this than to write that. Okay, let's take this a little bit further. Given that we're explicitly initializing players to 0, why would we do that? This is the way of saying the value is 0. Everyone knows that the 0 value for an integer is 0. We shouldn't need to explicitly say that. It's kind of it's confusing because as a reader, I'm wondering, why are we explicitly initializing this thing to the value that the compiler will give it itself? It's like it's a smell. It's like, why? What's so special about this? Why, like, this is already 0. Why do I need to say, like, kind of hard code it and say, really, really, really is 0? So that's kind of the argument about, that kind of brings you back to this form. So when declaring but not initializing, this is the form to use. What about this second statement? We can't do this. We can't say var things equals nil. So we can't go from this form and simplify it in the way that we did the two previous ones. We can't elide the type on the left. And this is because nil doesn't have a type. Talk a little bit about that later. And this is interesting because now we have a choice. Now, because we can't use that form, we have a choice. We have to say, do we want a nil slice of thing, or do we want an empty slice of thing? These are depending on your point of view, either very different or subtly different. I mean, when you're iterating over them, a nil slice and a slice of 0 elements has no effect, but it can be detected by things like reflection and stuff like that. So if we actually wanted the later form, this is not the 0 value for a slice. The 0 value for a slice is nil. So if we actually wanted that things was an initialized slice with no elements in it, then we have to say, I want a slice with no elements in it. And that kind of leads me back to the short declaration form. We're not, this is the 0 value form of this initialization. This is not. This is explicitly choosing, I need it to be a slice of no elements. Can't be the zero value. It has to be something different. And so because of that, we want to make it clear to the reader that things can't just be nil. It has to actually be a slice that has no elements in it at the moment. We want to make that clear to the reader because there's something special about that property. And again, this brings us to the third declaration. We're initializing thing to a pointer to a thing. I should have given it a better name. There's too many things here. Which is both explicitly initializing, like that's not the zero value, and introduces the uncommon use of new. This is a thing that flares up in Go every couple of years when people discover that there's new and make. And they're very upset that we have two very similar concepts, but two names for a very similar concept. And so it is fairly uncommon to see new used in common Go code. Because if we recognize that this is not the zero value, so we use the short declaration form, and we're assigning thing to a pointer to a thing using this uncommon new syntax. Now we can remove this uncommon use of new with the compact literal syntax, which does exactly the same thing. Well, it has the same result. We say it in a different way. And this is why people get upset about new. They're like, well, you don't need it. Like you can do everything you need without new. But again, this means that we're explicitly initializing thing to be a pointer to a thing, but you see there's no information between those curly braces. We're using the compact literal form, but we're not giving any fields. So we're not actually initializing it to a specific value. We're just using a very complicated way of just saying we want to declare a thing and we want to take its address. And again, thing is just a value, it has the zero value, and we take its address. So there was a lot of talking in there. But this is all to try and, this was my thought process of like, how can I make sense of the different ways we have to initialize in Go and kind of boil it down to two. You can't boil it down to one. There is no style, there is no way you can compress all these requirements onto one. But we can probably get it down to, in the general case, two. One is when you want things to be initialized to their zero value, and when you actually want to give them a value. And this is the style that I try to follow. Now, of course, in trying to make any argument of like, follow this rule, there are exceptions. Here's a really good example here. Here we have min and max, which is 0 and 100. So if I followed my advice before, we would end up with this. Well, min, we want it to be 0, so we let it take the 0 value. But max, we want it to be a different value, we want it to be 1,000, so we explicitly initialize it using the short declaration form. And this looks terrible. It's like we have two lines, two related declarations, but using different syntaxes. This is terrible. By strictly adhering to this kind of hard and fast rule, it looks weird. Like it's weird, one of them's initialized, one of them isn't. It's confusing to the reader. So in this case, maybe it would be better to write this. Min and max is 0 and 1,000. Super clear that even though we're breaking our rule about never initialize something to its zero value, in this case it's very, very clear to the reader that there's 0 and 100. And perhaps, this is extrapolating a lot, perhaps this is a clue that actually they're not variables, they should maybe be constants. And again, you can, maybe this falls out of writing your code. And I want to give a counterexample, which is going all the way back up to here. This form and this form are identical. So why would I use this latter form? And the thing I want to fall back on is this idea I think it comes from one of the books that Brian Kernighan wrote, either C Programming Language or the one that he wrote with PJ Plowder, which is when there is something complicated going on, make it really obvious. If something is complicated, if something needs to be initialized in a very specific way, make it look obvious, make it look complicated. For example, like this one here, var length uint32 some hex constant. And the reason I'm arguing this form here, this long verbose form, versus this form, is that I want it to be very explicit that length has to be uint32, and this is an important property of this made-up example. And so I'm deliberately breaking my rule to make it very clear to the reader there's something very important about length. I think that this form is too easy for someone to just like, well, this is an untyped constant, so it doesn't need to be cast to a uint32 or converted to a uint32. I can just delete that because it'll still work. Because like wherever length is used, it will get the right type. So there's just in some ways I'm contradicting myself because I said here are two ways, but I'm also saying when there is something unique about a declaration, and this stuff generally comes up not when you're dealing with business logic code, but when you're dealing with stuff on the network, stuff on the wire, stuff encoded or bit packed or stuff like that. So in the cases where the actual representation of the data is important, kind of make it obvious to the reader. This is some general advice about, so say you have the way that you like to see your declarations work and initialize. Like I've been very clear that I have a very specific style that I like. I think it works for me. I think it's useful. But we all work together in teams. We all work on multiple projects, especially if you contribute upstream to various open source projects or share code amongst people. You're going to find cases where your style doesn't really match the prevailing style in the file. And the advice I have is in this compromise because that's more important. That it's more important for the code to be consistent overall. Use a consistent initialization naming style, even if it's not your favorite, because again, you're not the only reader. This is something that occasionally comes up in code review, where people will write their own functions in their own format that isn't really the same as the rest of the file. In my opinion, it is, even if it's not your preferred style, it's more important to follow the prevailing style of whatever project you're in, given the very limited scope that we have inside Go format, than to stick to your guns and say, try and wheel out this advice and say, look, it's only a 5-line function, it should have short identifiers. If all of the other functions inside the file or the package use long identifiers, I think it's more important to be consistent. For example, if you used my advice, you'd have, here's a short piece of code that violates the rules using the short declaration for explicit declarations. So it's trying to use only the short initializer, and we've kind of got a couple of cases here where we're initializing a boolean to false and free to it. It does have a type, but it's still 0. So in that case, maybe using this kind of overall var block, even though some are initialized and some are not, might be more harmonious. Let's have a look at another example. There are lots of places inside Go, certainly inside the standard library and kind of code written in the kind of conventional Google style, where we actually forgo this advice. For example, if you have a connection returned from net.dial, it's almost always called con rather than C, just because that's the way. Where bizarrely listeners are always L. This is just kind of the local style. Like when and so if you find yourself working in a project that is doing some kind of networking type stuff, this is the predominant style. And kind of to repeat that advice earlier, if you had a program which This is a kind of very simple proxy. It only works on one connection at a time. Rather than calling them con, we call it client and upstream. So instead of calling them con1 and con2 and having to remember, we copy from con1 to con2 and from con1 back to con2. Like you can see it, it'd be very easy to transpose those, get them in the wrong order. By calling them client and upstream or source and target, it's very clear that you want one from the source to the target and from the target to the source. And even better than that, you don't even need to remember which order copy works. Is it copy from this into that? As long as you have both forms there, it'll work. I've talked a lot about avoid your names conflicting with local variables. Is basically don't shadow good variable names with your packages. And on that, it's important to remember that even though inside the package, the name of the type or the variable or the function or the method that you write, you think of it as, so for example, in my project, I have a thing which builds a big tree, and its name is builder. Inside the package, it's called builder. But the name of the package is actually DAG. So all the time, when anybody else is talking about it, anywhere else in the program, it's always the DAG builder. The takeaway there is just to remember that the name that you work on inside a package is incomplete. It always has a second component, which is the name of the package. Whenever anybody else outside the package that you're working on uses your types, they always refer to them in this fully qualified name. It's always package.symbol. Now, the name never includes the quote-unquote full path. Like it's never application server v2 cache. It's just cache. And API's meta v1, a package like an import API's meta v1 isn't the v1 package of the meta package of the API. It's just v1. And because of that, this style, which is unfortunately very prevalent in Kubernetes, means that you have a lot of conflicts. All of the Kubernetes types each live in their own package, all called v1. And so whenever you import them, you always end up with a lot of renaming. We've got a lot of v2s in here. v2 here, v2 there, v2 here. And so you can see that to even be able to use them, we have to rename them. And the advice I want to come there is to remember that the name of your type isn't enough. It's the package and your type. Think of them together and make sure that the combination of both of them is unique. Some stuff about reducing repetition, I'm sure we've covered a lot of that. But just on that subject of thinking about the symbol and the package's name together, avoid the repetition that can come with this. For example, nothing in the HTTP package starts with HTTP. It's not net HTTP open. Yeah, nothing in the HTTP package starts with that because the author of that package knew that whenever you talk about it, it would be HTTP dot. You'd always have to say that in the front. There's an example a little further on where I actually go into that. So the next item I want to talk about is commentary, like the comments on your code. Because I think that they actually have, we have a very strong tradition of commenting in Go. Like because of GoDoc pulls its code out of your source code, the canonical documentation for anything that you do in a Go package can actually live in its source code. Like there is no requirement to maintain parallel documentation. And I personally believe that the greater the distance between a thing and the documentation of that thing, the greater that distance, the better the chance that they will be out of date. And so we have tools inside Go that let us document at both the package level and the function level, the exact canonical documentation for that. It's not quite as ornate as JavaDoc or things like that. It's more, I think it's more kind of in the same line as Python's here docs. But comments are very important in Go code, and we have a strong tradition of those. And I've come to think over the last couple of years that there are really three types of comments. The first one is the comment should explain what a thing does. The second one is the comment should explain how the thing does what it does. And the third one is it should explain why the thing is why it is. And these are not just like three different ways of saying the same thing. They're actually very different ideas. This first form, the comment should explain what the thing does, is what we do for writing documentation on methods and packages. Open opens the named file for reading. Successful, it does a thing. This is your classic Go doc. This is the documentation. This is the description of what the thing does. If it wasn't obvious from the name, like the name open, here's a little bit more information about what it does. Pretty uncontroversial. The second form, the how, is the kind of comment that you're going to see inside a function. What are we doing? How does it do the thing that we're doing? In this made-up example here, I think this was from some code in GB that I grabbed a long time ago. And I'm just leaving a note to myself to say, in this little block here, we're queuing all the dependent actions. So this is basically building a graph of actions that need the children of the tree to complete before they roll up there. But it's not, I think in the function it was not super clear what's happening. So this is a little thing that says, this is how it's doing. This is an little explanation for the reader of what's going on right now. But the third form of comment, the why comment, I think is unique. And I'm sure you've all done it, but I wanted to classify them to point out their differences. This why form it doesn't replace the what and the how, but it exists to explain why the code is why it is. And this example here, this is from the product that I work on. Sorry about the line wrapping. And it's a very specific thing that Envoy does. By default, its value for panic threshold is not what we want. Don't ask me why. Its default is to, I think it has a threshold of 50% or something like that. So in this case, we explicitly want to set it to 0. And as a reader, you would be confused by it. You may be confused by this, because why are we assigning a 0%? Like, why are we explicitly going out of our way to say 0? And the answer is that by default, the default is not 0. And so this kind of comment, the why comment, is, I can only say it exists to record these kind of hard-won battles of like debugging things, of the actual business logic of like, we have to, we had a problem here and this is how we had to work around it. This is exactly where that code came from. We didn't want Envoy's bizarre 50% behavior. And so this is the why comment is an opportunity for you to give clues to the reader of like, you may be confused by this. Here's a link to the issue. Here's a link to the issue where we debugged it. Like this one comes with a link to the documentation that explains what this parameter does. This just note that comment. I say that comments are associative. They glue to the next thing on. And so always in these examples, the comment directly precedes the thing it does. Basically, I'm just saying don't put a space there. I'm sure this is perhaps overdoing it here, but always document your public symbols. Like that's what we do. There are some good rules from the Google Style Guide. Like any public function that is not obvious and short must be commented. And they say, and so this is in your own code. Any function in a library, period, must be commented no matter how long or complex it is. So here's an example of that. We all know this Go commenting style. There is possibly one exception to the rule, and this is where I may be bringing my own bias here. But we have the vetting tools and a bunch of the linters get really stroppy when we have a public method which exists to implement an interface and doesn't have a comment. And the reason I don't find these particularly useful is they're almost like the only way to make the linter shut up is to say read implements the IO reader interface. Like that makes them shut up, but it tells us it adds no value. Of course it fulfills the interface. We know that. That's why we added it. It doesn't say anything useful. It just kind of is noise. And I want to give an example of that from the standard library that I think follows a much more sensible pattern. So we have the limit reader type, which takes a reader and an amount to limit it by, and returns a limit reader type. We have some documentation on the limit reader itself, because it's a public type, so it has some documentation. But in the actual implementation of read, you'll note that they didn't put any documentation there. And that's fine, because limit reader read directly follows where it's using, and there's a very big comment that explains exactly, you're going to get a limit reader, and it's going to be used for limiting reading. So there's no reason, like what comment would we add here? Like just read, like most of the examples I see in Go code, go to the IO reader Go doc and just copy the first line and put it there. I just don't think it adds very much. But if you want to shut up the linters, you can do that as well. The next thing I want to talk about are comments on variables and constants. And I argue that they should describe their contents. They shouldn't describe how they're used. This is something that I see somewhat often. So the goal of the comment here is to describe the contents, not how you're going to use those contents. For example here, we explain why it's 6. If anyone gets the XKCD joke there. We don't explain where you would use random number. Yeah, as I say, the comment doesn't describe where random number will be used. This is deliberate. Random number, it's public, so it can be used many, many times. It can be used in ways that we can't enforce and we can't record. So there's just, rather than maintaining this ridiculous documentation on where all the places you should use this random number value, we leave that to the name. The name of the constant should be a guide, the appropriate use of it for potential users. It's called random number. You don't need to say use this when you need a random number. It's right there in the name. Here are some examples from the HTTP package. And again, talking about the commentary. Got HTTP status continue, status switching protocol, processing. And think about if we didn't have this comment here. These would just be numbers, 100, 101, 102, 200. These are just untyped constants. But the important thing is, in the context of HTTP, the number 100 has a very important meaning. It means continue. And it's defined in this particular RFC at section 621. And so the comment is included with the declaration just to help the reader who maybe isn't as au fait with HTTP as I am, that this is why the number is 100. Like, why is number 100 assigned to status continue? The answer is go read the RFC. Now, you have an interesting case where you have variables that aren't initialized that have comments. This is an example from the compiler. Now, the comment is descriptive. It says what this variable indicates, like size calculations are disabled, and also says when it's going to kind of happen. And it gives a hint to the reader, go and see this thing called doWidth, which is obviously the function responsible for flicking this Boolean between true and false. And there's kind of a hint there that this comment breaks all those rules that I just suggested. It tells you where it's used rather than what it contains. It tells you, it gives them a hint to go that doWidth and size calculation are entwined. And so this comment actually, I think, is an example of a code smell. Like, it works like that. This has been in the code base for a long time, but in reading it, I get a sense that this is in the wrong place. This is actually a hack. This thing is a hack that it's been in there for a long time, but it actually exists because it's a piece of global state that different parts of the compiler use. They argue about the state of this value and disables or enables type checking. So the fact that it's this kind of global thing with this bizarre comment really gives you a hint that it's a design smell. There's this great tip from Kate Gregory that oftentimes when you have a poorly named value, you will very close by actually find a better name for it. So here's an example. Registry is a registry of SQL drivers. Now, perhaps the comment was added because registry doesn't explain enough about its purpose. Like, it's a registry of what? By renaming the variable to SQL drivers, it's now very clear what it contains. And importantly, you don't need the code, you don't need the comment anymore. If you want to go even further, maybe you call it SQL drivers registry. But sometimes we find better names for variables right there in the commentary with it. Here's another perhaps contrived example. We have a counter I, and the comment above it says total number in V. So obviously, as we go through V, we're accumulating an I, and then we return the ith value. Wouldn't it just be easier to call it total? Then you don't need a comment. Even though I need to fix that example, but you can see where I'm going with that. That if this was total plus equals n, it's very, very clear to the reader, without any comment necessary, that total is our accumulator. Now, I think this advice applies in the opposite when it comes to functions and methods. Where I said the comment on a variable should describe its contents, not what you do with it. It's the opposite for a function. Comments on function signatures should describe what the function intends to do, not how it does it. So we don't want to describe the contents, the implementation. We want to describe what it does, or more importantly, what it will do for you. Obviously, those comments should describe like the inputs and the outputs, but again, not be prescriptive about how those inputs and outputs should be used. Like, I find it quite common to read commentary that talks about something like, you should check the return value to make sure. No, that's somebody else's job. Just explain what that return value will contain, and they can figure it out themselves. And this is a nice tip from Dave Thomas, pragmatic programmer, author of The Pragmatic Programmer. And he says, he gave a talk about his way that he sits and writes down and decomposes a program. And the way that he decomposes it is he starts to look at those conjoining words, or and things like else, like any of those conjoining words. And he says that they're a smell. If you sit down and you write the comment before you write the function, and it contains like words like and or. So for example, this function returns a user or returns a default user. That's a smell that it's actually doing two different things. And this was the way that he tries to decompose his programs. When he writes a description for a function that does two things, he stops, he writes two separate functions, and then goes back, and the original function is now just the composition of both of those. This section is obviously named after this suggestion from Brian Kernighan. Don't comment bad code, just rewrite it. It's a little aspirational. Sometimes you don't have the luxury to refactor stuff. But the point is, it's not enough, like in industrial programming that we do, it's not enough to just write a big salty comment about how gross something is, and then be like, well, I commented it, if you stood in it, it's your own fault. If you encounter one of these comments, I believe that you should raise an issue in however you track issues, like reminders or Jira or GitHub issues or whatever you want, to refactor it later. Like, it's okay to live with this technical debt as long as you have some kind of assay of where it is. This is the very, very common style that we use, inherited from Go projects. There's nothing magical about to do, like it doesn't have any special meaning. Actually, maybe that's not true. I was going to say it certainly doesn't have a meaning to Go doc, but there are linters and tools now in the Go space that kind of will at least identify these things. And the common way is to say to do, and then at least in Go we put the name. And generally if it's me writing the comment, I put my own name. And the thing about the name is it's not that I'm promising to fix this. Like it's not David to do, come back and fix this. It is when you come across this comment in 6 months, you know who to ask about why it's there. Like I was the last person that touched it. And this is just the style that you'll see, certainly working on the standard library, that the to-do is not a promise that I'm going to fix it. It's just that I will probably be the best person to ask if you run across this. What would be a better form is actually what this example is missing, which is, yeah, you can have a little summary of what the problem is, but it should have like an issue number next to it, or like a JIRA number, or something like that, where the rest of the discussion is. It's very, very common in my project. We work very, very incrementally, that you partially fix or partially implement something. And so you should, in the cases where like they're not implemented or not finished, or we have kind of edge cases where the transformations are not complete, we leave issues to ourselves to say, rather than trying to figure out what goes in here, go and look in the issue to say what was left. This next section is poorly named. It's called Matters of Style, mainly because in trying to taxonomize the different suggestions that I had, these ones kind of, well, they stood by themselves, and the only kind of way of categorizing them I could say was that they are, well, matters of style in the way that style differs between people. So these are very opinionated suggestions, which are not enforced by our tooling, or which are not either very common or very resolved issues. Like their style, their fashion. For example, Go format has a lot of control over the horizontal white space, about where the closing braces go. I don't know if anybody's noticed that when you have an arithmetic or a logical operation, Go format will actually group things together by their precedence. So if you have different operators like plus and double bar and things like that, it will actually group them or space them out depending on their precedence. I mean, this is just a thing that it does. So Go format has a lot of control over the vertical white space, but that leaves open the question of, well, what do you do with horizontal white space? I'll give you an example from, there's a lot of white space here. And if Nick's watching, to be clear, I'm not picking on you, mate. But these are areas where people are going to disagree. Like, why is there a blank line at the top of this function? Why is there a blank line after that? These are points of like Go format solved so many of the style arguing issues. These are just places where we can have arguments again. So I want to offer some, or actually recommend some guidance again from the Google C++ guide, which is basically, and I apologize, this advice is very English specific. I don't know how paragraphs work in Hebrew, but the idea in English is that each paragraph, each group of sentences is separated from another by a blank line. And when constructing, when writing in English, each of these are basically ideas or parts of an idea that are both consistent with themselves and stand alone from each other. So one of the suggestions I have for using white space, like vertical white space, in your code is that, just as they say here, just as you begin each paragraph in a piece of written text, each paragraph is a new thought. With the line space, do so with a set of statements in a function. So I'll give you a different example. So this is a big helper. The route is main helper that kind of constructs a big data type. And the example I'm trying to give is that I'm breaking up the different parts of what this function does. Like its goal is take one type and return the Envoy version of the type. So it has to do a lot of different conversions. And each of the blank lines you see here breaks up the different ideas. For example, this first bit is building the initial data type. There's a whole bunch of helpers in here. And then break, new idea. Then we do something complicated with the host rewrite specifier. New line, we're done with that idea. Now we deal with something with WebSockets. New line, we're done with that idea. And you see that all of this is clustered together because all of this is the last idea on the function. That's all I really want to say. Yeah.
Would you say that this is a long function?
It is long, and it's always a battle. So, for example, one of the ways that we battled this is each of these is a little helper, which is actually like each of these, like you see here, these are always different strange data structures. There are also other ones of these. So we made it shorter by taking a lot of that kind of logic here and breaking it out into functions.
I wonder regarding the R and the RA, the variable names, which are very short.
Yeah, part of the problem here is to do with naming. The name of the type of the input is called route, and the name of the type of the output is very similar to it. It's a route. Like the word route exists too many times inside this, and this is something that we don't have a lot of control over because Envoy, these types are derived from gRPC, which is very verbose. And that puts us in a difficult position. I can't use lowercase route because that's actually an import somewhere else as well. And so we're kind of out of good identifiers. RA is a synonym for the route action, like maybe we call it route action. But the smell that I would identify with this code is not that it maybe is too long or combines too many things, but certainly is the inflexibility we have in choosing good local identifiers because all of the good ones have been used by, we can't use route, that's already been taken. There are a number of smells here. I will talk a bit about function length, but that was a very good question. This is really all I want to say about blank lines, because I think they are important when you have a function which, one function should only do one thing, but sometimes in doing that, you need to do it in several phases. First of all, you have your guard clauses where you set up your preconditions, then you have some body or some looping, and then you have some kind of finalization. So even in a function that does one thing, sometimes it does it in several steps. And a good way to break those steps up, this is just the way that I like to do it. Of course, how long should a function be? The eternal question. The answer that I like the best is from Kate Gregory, which is she gave an example where they were you find companies that have like a local style guide said, code must never be bigger than a page for whatever definition be, or never be bigger than a screen, but everyone's got a different sized laptop. And then they come up with it should never be bigger than 50 characters, never longer than 50 lines. But you will absolutely find a reasonable case that you need to use 51 lines. And that's like any arbitrary length, you'll always find good reasons why you can't keep that length. So I don't think those are useful kind of like hard and fast rules, like no more than 20 lines, no more than 51 lines. There'll always be a good reason to break that advice. This is a little bit of a conceited quote, but the reason I include it is this observation that it's not thinking about the design in terms of do or don't. Like don't make them too long. The real problem is mixing unrelated ideas, having a function that does more than one thing. I will let me expose my shame when I show you the worst function that I've written. This is so in our command. I'll just make it smaller so you can see. This is the main run logic. So do serve is like the if you figures to Cobra or something like that, they have like a command that you give to the CLI. So when all the flags are resolved, you call the command function. So this is do serve is the command function, and you can see that this function is so long. It actually has kind of like waypoints in it, like step 0, step 1, step 2. We do these things. We build up some more things. We have some more steps. We add some stuff. We are well aware of the length of this function being like this doesn't just compose 2 ideas. It composes, well, how many steps have we got? 11, 13, before, and then step 15, we actually start. So after doing 15 different things, we actually start. In the defense of this code, this is the only place we do this. This is the pattern of your command will bring together all the other objects. Will set up like it sets up all the Kubernetes things. It connects a whole bunch of things, and so even though this function might be long, we only ever do it once. This is, and I kind of have a suspicion that this code that exists in command, where you bring together all your logic, is going to be different. Like it is very declarative. So, as I say, it's okay to break the rules as long as you're honest with yourself. This is something that I'm sure all Go programmers have seen, but maybe you never really kind of put a name around it. And this is the pattern of returning early rather than nesting deeply. When I talk about nesting, I'm mainly talking about, if you think of languages that use an exception-based flow control, they bring the successful case, well, it has to be inside the block for the try and the catch, so it has to be at least indented 1 level. And that kind of leads to a style where you kind of nest your successful conditions, like the success path is moving further and further to the right. It's like, well, that's true, and we haven't had an exception, and that's true, and there's the actual logic in there. I'm not sure how many C# or Java programmers there are in the room, but this is a very common style that kind of falls out of the try-catch behavior. Now, we don't do this in Go. If anything, we do the opposite. I haven't got a link here, but Matt Ryer, and I can link to that. Oh, I do link to here. He gave this a name. He calls this line of sight coding. The idea is that the successful case doesn't disappear off to the right-hand side, nested in. It stays as close as it can to the left-hand side of the screen. And some of the ways that we achieve this are guard clauses. So, for example, a guard clause is basically just looking for a precondition that's failed. So, in buffer unread rune, we just check that last rune is greater than op invalid, and if it's not, then we return early. So the thing that we know here is once we get to this point, last read, we know this precondition is true. We have another bit of logic and some more logic here. Now, try to give an example, I rewrote this function nesting the success condition. Rather than the success condition keeping on the left-hand side, I rewrote it so the success condition was nested. And this is what it looks like. First of all, we have to turn the condition around. So if last read greater than op invalid, which is true, otherwise if it's false, at the end we return. So we've had to turn the logic inside out. And this means that this is the success path here. And it means that this return nil here is actually the success case here. We had to hunt and find it. Whereas in the more traditional Go style, the success is always the last thing that happens. Your function always ends in the successful case. Yes? Okay, so the question is, branches predicted versus branches unpredicted is usually inferred by the condition being true or the condition being false. I only believe, I can't be absolute on this because this does change quite a bit, that we tell the compiler that the branch is unlikely. So if there was a performance difference, this is the faster form, although really honestly fast is very, very small difference. Yes, I believe that branches are predicted not taken. Maybe I like that. Maybe there's a double negative. But basically, this is the uncommon path. We don't expect the error. As we move down the function, we're building confidence that all the preconditions have been met. We don't have to check again. We don't have to check again. What did I write here? Yeah. To find the successful exit condition, this one here, we have to carefully read the braces and match them. Like, it's important that the success case doesn't happen here in the innermost one. It's actually kind of tucked away here. So clearly rewriting it into this form was not a success, which is good because our standard Go form of check preconditions, or the unlikely case, and keeping the success path on the left-hand side pays benefits. That's why we prefer guard clauses and returning it early. I think the zero value is one of the really underrated things in Go. There are other languages where you don't get it either via convention or just because of some things that fell out of the very early C linking model. But Go explicitly initializing every value for it, whether you ask to it or not, means that we can take advantage of this. We don't need to construct every type. They're kind of valid by construction often. For example here, sync.mutex. It contains two unexported fields, which I don't have linked here, that have things to do with its state. Now, because the author of sync.mutex arranged it, when those two values are zero, that's valid. That is a valid unlocked mutex. It's been deliberately written to work that way, which means that you can just declare a mutex anytime. You don't need to initialize it. And that means you can embed it in other types and get that same property. So for example, here when we declare a new myint, which is embedded, has both a value and a mutex inside that, it is usable immediately without any explicit initialization. One of the takeaways of this is if you ever see any code that takes a pointer to a sync.mutex, that is a design smell for two reasons. One, that means you can't do this form. The value is not ready to be locked. Like that mutex isn't just unlocked, it's nil. Like the default value of a pointer to a sync mutex is nil, which will panic if you try and use it. So that means the type that may be embedded a sync.mutex by a pointer isn't usable without explicit initialization. And that's kind of a trap. The other one is that a pointer to a mutex means that you're sharing somebody else's mutex. That's a really, like that is generally where the design smell shows up further. It is trying to extend the thing that a lock locks over. So I want to use somebody else's lock to lock access to my variable, which is really what it's saying here. I want to have a pointer to somebody else's lock so I can be covered by their guarantee. And that is just generally a big design smell. So just as an aside, if you ever see a pointer to a sync.mutex, you should be asking questions why this is why it is. Hopefully, in most cases, it's just a misunderstanding. People thought this is a complex type, we should have a pointer to it. But the much easier answer is just to embed it directly. Another thing which hopefully people take advantage all the time is a Byte Buffer, which is a kind of string builder type thing, is usable without any initialization. I know there are forms where you can say bytes new buffer and then pass in either a background buffer to use or to base off something else. But in its default form, you just say var b bytes buffer. You can write data to it. It doesn't need to be a pointer to a bytes buffer. This will work perfectly fine. And if you do need to pass it into an interface, you can take its address right there. Slices have an extremely useful zero value. And the reason for this is We can't directly represent slice in Go's type system, but we can talk about it basically. Each slice is 3 words. It's a pointer to an array of the underlying elements of the slice. This is what we can't express in Go. And it has a length and a capacity. Now, these two will default to 0. That's their 0 value. And a pointer to an array, its 0 value is nil. So this means unless you need to specify the size, you don't need to explicitly make a slice. You can just declare it. This is the same as that, is almost the same as that. Pardon me. These two are identical, and they're very similar to that. The difference, as I said before, is that this is the backing array points to nil in this case, whereas the backing array points to an array of 0 elements. And as you see, it is possible to detect this in Go. Honestly, unless you're working with reflection or writing and encoding from a structure to some kind of wire format, you will never need to think about the difference of this. It really doesn't matter. You can also take advantage of this property, although I think this example is slightly. This is a pattern that we follow in Contour. I'm not sure how widespread it is, but because the receiver of a method is just another parameter in Go. There's nothing special about it. There's no vtable. There's no pointer to a parent. It is totally fine to call a method on a nil value. So that means that you can put default behavior on a on struct. So for example here, config, even though that's nil, is going to return some default parameters. If we explicitly initialize it, it's going to return a different value. But this code works just out of the box. So you can kind of have default behavior. Like if I don't initialize this to something, let it have its default. There's configuration structs in general are quite complicated in Go, but that's a nice property of the 0 value for a pointer. This is an interesting one that definitely I think it does confuse people coming from other languages that do have a very strong understanding of how pointers work in their particular language, or equally confusing when you have a language like, say, Java, where there are references but you don't really get to control them. Like there's no notion in Java of dereferencing an object. You just don't have that kind of control. So one of the things in Go is that we can declare the receiver to be a value type or a pointer type. What I mean is, like, the receiver is, actually let me do this here. Is everybody clear what I mean when I say value receiver and pointer receiver? Is that okay? Okay, cool. And again, this is a case where we have a choice. Just like in declaration and initialization, we have a choice. And we're presented with a choice. That means 50% of people are going to do A and 50% of people are going to do B. What is the reasonable advice for should I put the method on the value type or on the pointer type? There are some background suggestions. For example, let me actually work on this a little bit more. I'm sorry for calling them T's. Like they should have better names, but I'm working quickly. T. Okay. What's this going to print? Is this going to print 0 or 1?
0.
Anybody think it will print 1? You're correct. It will print 0. And the reason it will print 0 is that this is a copy. Methods and functions are identical. It's just that the parameter, the receiver, moves, rather than being specified here, we put it over there. But it has exactly the same behavior. So here we're passing in a copy of T, not passing in the address of T, we're actually copying it and passing a copy. So when we increment it, we're incrementing the copy and then throwing away that copy. So that's why this increment doesn't do anything. If we want it to actually do something, we have to pass in a pointer to the T. Now it does something. So the advice we can take away is that you want to use a pointer receiver when the caller will change something on the receiver. Like I've shown you that if you don't have a pointer to the receiver, you can't make any changes to it. Maybe you could also say that pointer receivers are when you care about the state, or you want to mutate the state of this thing. The inverse is also true. One of the few examples in the standard library is time.time. By design, methods on time, you'll see here, all work on the value type, not the pointer type, because time is designed to be immutable. So every one of these that are called on, they get a copy, although the copy is usually elided. They get a copy of the receiver. So times are immutable. Every time you get a time.new, it's immutable. I think the Go developers learnt their mistake from Java. So maybe that's some advice. Methods that mutate the receiver obviously need to be pointers. The methods that don't mutate the receiver don't need to be pointers. Now, Koenig and Donovan, the GOPL book. Hopefully everyone knows this book. If you're asking me for a book to learn Go, buy that one. It's written by the same person who wrote the C book. That's all the recommendation you need. Now their argument is that to break this impasse between we have some pointer things and some value type things, they recommend if some of your methods have pointer things and some of your if some of your methods have pointer receivers, then all of your methods should have pointer receivers. This isn't just for consistency. You can have problems, specifically data races, because copying. Let me show you in this example. Let's embed a mutex in this T. We don't need to use it. Oops. Hopefully that will fire us. So the reason I did this is that the playground runs vet on any code before it executes it. And it's saying that because this method is declared on value, not a pointer, we're passing a lock by value. We're actually making a copy of that lock. This T is a copy of that T. So we haven't just copied the value V, we've copied the lock as well. And if you copy a lock and you're locking an independent copy, it has no value. So this is part of Koenig and Donovan's advice, that if some of your methods have pointer receivers, then all of them should, because if you mix and match, you're going to run up against problems like this. Again, types that are specifically designed to be value types, like the time and duration types, play a little bit fast and loose with this advice, but they're very carefully designed. They're very carefully designed to do this. So the general advice is use pointer receivers. If you use pointer receivers on one thing, the rest should follow suit. I want to close this section quickly, and I'm not really happy with the names of these suggestions. They're like avoid this, avoid that, avoid a third thing. But putting that aside, I want to give some of my rationale for why, for example, named return values, of why I try to avoid them. Does everybody know what I mean by a named return value? A named return value is, let's just make a function. These are named return values. Like, these are not the formal parameters. These are names we give to the return value, which means that you don't need to declare them. You can just say, you can just assign to them directly. Now, the reason I bring this up is that I think that named return values kind of violate some of this advice about the separation between the declaration and the use. In Go, we try and keep the declaration of a variable and then use it straight away. We don't, that tradition that grew out of C and actually grew out of Pascal and Algol before it, where all the variables for a function are declared way at the top and then used later on. And the reason for that was that to make the linkers, to make the compilers one pass, they couldn't remember a variable, declaration. They had to all happen at the top and then be used because there wasn't enough memory to go back and reparse that bit. Obviously, that hasn't been a problem for decades. So in Go, we try and keep the declaration and use of a variable as close as you can. You see in all my examples, if I was summing into a variable, or I was assigning to a slice or appending to a slice, it was declared directly above it. And the problem with named return values is they break that idea. Because the declaration has to happen at the top of the function, as that function gets longer, the distance between S and error declared and where they're used grows, and we can't control that. So they increase the risk of shadowing, and they enable the use of naked returns, which I'll talk about next. I think overall, naming return arguments is a net negative to readability, if for no other reason than it is yet another form of declaration. Like the 6 we saw before, this is a 7th. And for me, when I'm reading code and I see named return values, that's a sign to me that this code is perhaps trying to do something very clever, and I need to look at it very closely. And again, the clever thing this code might be doing is trying to make itself too short. It might be trying to avoid, like, reduce the length of the function by like 1 line by using this uncommon construct. And I don't think that really pays for itself. There is one example where you do need to name your return arguments if you want to do something like this, which is, and this example came out of one of the arguments about try, which was, well, the try, because it returns directly to the caller, we don't have a chance to annotate our errors. And this was one of the solutions proposed, which is kind of gross for two reasons. First, so the way this works is we always run this defer at the end of the function, no matter how it finishes. And because we've named the error value, we can, because it's now declared at this point, we can now capture it. And so this error is not that error. This is the super confusing thing about it. These are different. This is declared in a smaller scope. This error is actually the return value just on the way out of the function. And we can grab it, we can check it for nil, and if it's not nil, then we can kind of append it. And hopefully you can see that this is quite magical. Like, it took a few minutes for me to explain what this is doing, and that means every time you have to read it, every time you have to justify it in code review, every time somebody new joins the team, they're like, what is this? How does this work? So there are some places where named return arguments can be used, but I don't really think They help. Yeah, so generally named return values let you write your function a little teeny weeny bit shorter. And if that's really the only reason, maybe they don't pay for themselves. Yes?
I think the other reason I saw was with the recover. You want to change the property.
Yes, I think I actually talk about this next. Recover is similar to this kind of defer thing. Like recover can only happen in a defer. And again, the same thing is you want to grab the argument that may have been declared later on. I know it's in here somewhere. Similarly, named return arguments enable this pattern called a naked return. It's just a word that people come up with. And when we say naked, this function requires 2 return parameters. But we're actually returning none here. That's what, I can't actually remember who called it naked returns. But this is, it's kind of inconsistent. We're relying on error, initialized up here, to be filled out. And then the return here says, don't change it. It's fine, it's already been filled out. So instead of, all this is saving is letting you whatever the value of file is, which is, it's avoiding typing that. So just as there are many ways of declaring, now all of a sudden we have a different way of returning from a function, which you have to remember. And you have to say, okay, at this point, what is the closest scope that is declared error? Just as a point of concern, that does something completely different. One character change, and it shadows this error. You can see there's a lot of ways this can go subtly wrong. And even more inconsistent, we have 2 return statements. One of them returns no arguments, one of them which actually returns 2 arguments implicitly. So like in this 6-line function, there are a bunch of things that the reader has to know just about this quite obscure corner case of Go. And so the suggestion I would have, like if you decide that you must use naked returns, it's something about you have a very complicated error handling or recovery path, don't mix and match them. Either always use a naked return inside a function or never use one. Certainly don't mix and match them. That's just a recipe for confusion. Talking again about initialization, we have this, because Go, unlike Java or C++ or C#, doesn't have constructors in the way that those languages do. Like constructors are a specific thing that take the role of initializing a value in memory before it's released to the rest of the system. We don't really have that. Like you have a function that can return an initialized thing, but it's not a constructor. So what that can mean is that it is possible in designs to create values which are not completely initialized. Here's a super simple case. We declare user count an integer, and it's initially 0. And then we immediately set it to the actual number of users it should be. And this is just confusing because you're like, well, why do we declare it and then overwrite it? Surely it would be simpler to just write, user count : equals count of user. And that's a very simple case of incomplete initialization. If we stop the program here, we inserted some lines in between this, user count isn't correctly initialized. It doesn't hold the right value. So it's incomplete. This pattern tends to show up much more often, obviously, when you have structs, because like this example, it either holds a value or it doesn't. It's just a primitive. Here, we have some kind of virtual host object. It has a name, and it has some route objects underneath it. First of all, we give it a name, so we initialize one of the fields, and then we do some more logic, like we get the routes for the host name, and we range over those, and we append them on the routes, and then we return the whole thing. And this is an example of incomplete initialization. because at this point, the vhost object, if we returned from it or there was, the logic got confused so that like the return happened here, it's missing its routes, it's incomplete, it hasn't been fully initialized. This is where we can rewrite it, and I agree that it is slightly longer, but at no point here is there a vhost object which is incomplete. First of all, we just get the host name, I just wrote it there. We declare something to hold our routes. We build up the route structure, and then we return right at the end here a new virtual host with a fully initialized host name and a fully initialized routes. And so this means that there can never be a virtual host that is kind of half initialized. I want to show you an example from my project where we had some discussion about it. And this, again, this is a small trivial example, but obviously the more state a structure has, the more chance it has to be internally inconsistent. Let me remember where it was. Yeah, so this is the smell that that I see here. So we have this function called cluster defaults that makes this cluster type. It fills out some of the fields, and then we go back and we fill out some more of the fields, and then we go back and we fill out some more of the fields, and that means that there's a risk. There's the thing that differs this block from that block is that these are kind of conditional. Depending on does it have a name, we have to do logic A or logic B. So there's no way that we can collapse that. But up here, there's no reason that we return a partially constructed cluster and then finish it off up here. All of these values are derived from the ones on the side. We could simply pass those in here and return a complete initialized thing. And part of the discussion I had about this when this change went in is that I would really like it so that that we can never ever return one of these things that's incompletely initialized. And as you can see, that discussion is still ongoing. But one place where this does show up is, and I'm not sure which language kind of community it comes from. I can't put my finger on that, but it is quite common to see Go code, it's obviously being transliterated from something else, that you declare a value and then you call some kind of initialization method on it. So you make one and then you set it up. And the problem there is, if you forget the setup, well then you have an invalid value and it's leaked out into your system, and good luck tracking that down. And there's also questions of what happens if that initialization is called twice? What happens if someone sees that and like, oh, I want to reuse this object, I'll just reinitialize it. It's putting a lot of very subtle logic into initialization, which really, if there was no way to create one of these objects in a way that was incomplete, you would never have to have that argument. So my suggestion is try to avoid these kind of patterns of creating values that are half initialized, with the promise of like the caller has to do some extra work to finish that initialization off. Because if they forget, then you're in a bit of trouble. Yes?
There's this pattern which I've seen in a few places where you have like a private field in the struct, and then like there's a flag that's been initialized or not. You can have a Boolean flag saying that can only be initialized from within an init function of the flag, and then you know if it's being kind of initialized properly or not. Yeah,
I don't know how I feel about that. It seems like taking one problem and making it worse. Generally these come up when you're interfacing with external systems. I want to be very, very polite to our guests here, but the AWS API is one of the worst offenders of this. That the types that it returns need to be initialized, and that is because that API is automatically generated from a definition which has to apply to a bunch of languages. So generally you find these patterns happen when you're kind of at the interface boundaries with a library that somebody else provided you with, and they haven't done the work to make their types properly initialized up front. So there's always this, I'm going to give you like new thing or return a new thing, don't forget to initialize it, because if you don't, you're in trouble. The last point in this block is some advice about finalization. Do people use finalization in their code? Yeah, a little bit. Again, this is my advice from spending too much time in the runtime logic. Like, finalization in any language is a facility when you can say, given that the garbage collector owns reclaiming memory, let's just put a little placeholder on this object to say, just at the point you're about to reclaim it, run some extra logic. And this is like super seductive. You can you can say, if that resource falls out of scope, close the file that was connected to it. This is really attractive. The problem is that finalization is not guaranteed to run. It's not guaranteed to run in the spec. There is no guarantee that if you attach a finalizer to an object and then you nil out that reference, so there's nothing left of it, it will run within some bounded period of time. As Rick Hudson, who wrote the garbage collector and who wrote the finalizer, says, doesn't guarantee the finalizer will run before your program terminates, because finalization is tied to garbage collection. And there's a competing, there are two forces opposed to each other. You want to keep your garbage collection cycles down. You want to produce as little garbage as you can and run garbage collection as least as possible. But finalization doesn't run until your garbage collection runs. So as your heap grows, the amount of finalization that happens slows down. And in fact, I don't have the reference to hand, but at one point Dmitry Vyakov said, we could just delete the finalization code and we would not be changing the spec, because the spec doesn't guarantee the finalizers would run. Now, there's only one place that I know of here, and there is a finalizer in every time you open a new file or you get a file object, there is a finalizer attached to that. And so, if that thing accidentally leaks out of scope, it will be closed. Brad has said, on balance, that was a mistake for two reasons. One, finalization isn't guaranteed to run, so people are depending, if they're expecting that when garbage collection runs, any open file handles will be closed. And the other one is that really what that logic should have done is if the file is not closed, the finalizer should panic and crash the program. Because that's really what you want to see. It's not, oh, I forgot to close it. Oh, it's okay, the garbage collector did it for me. It's, I lost track of that resource. I leaked that file handle, and someone just cleaned up for it quietly, and I never had to know about it. So, in my opinion, try to avoid programs that depend on finalization for correctness. But, yes?
Would you recommend using Defer for things that you would like to see in finalizer?
Good question. Yeah, defer is useful if the object lives within like the lifetime of a scope. Like, function starts, you allocate the object, you do everything you need to, possibly going down to some functions, but its lifetime is bounded by that function call. Yes, defer is absolutely the right tool for that. I talk at the end of this document about how to tie the lifetime of resources to the lifetime of Go routines, and so basically manage the lifetime of resources with a Go routine. So that's what I recommend. Now, again, with all advice, if you do have to do some, where finalization seems to be used quite a lot is where people have to use CGO, and unfortunately, you have many problems when you're using CGO. But the important thing to remember is that the finalization will run eventually, but eventually may be far too late. For example, if you're opening files and then letting them fall out of scope and hoping they'll be closed, there's a fundamental limit to how many files you can have open. It's a couple of thousand. Even if it's 100,000, that still means that garbage collection and finalization has to complete while there are less than 100,000 files open in your program. And that's a really weak guarantee to rely on, that as your program does more work, it's going to reap the resources that you're leaking at a reasonable rate so you don't run out of them. So I'm not even sure if this advice should be in here. Like, I see finalization in the business logic that I work on, which is not complicated, used very infrequently. But it is important to realize that you can't say, I nilled that out. It's going to be closed soon, because soon is not defined anywhere in the Go spec. Speaking about nil, let's talk all about nil. Because nil is the most bizarre thing in Go. It's one of those kind of quantum states that the more you look at it, the less you know about it. There's no nil type. Nil does not have a type. Yet you can compare it to anything with the type. You can't alias nil to another thing. So you can't say type T nil, where you can say type T int, because nil doesn't have a type. Nil can be assigned to a value and it can be compared to a value, but nil cannot be compared to itself. This doesn't compile. Like you would expect this to be the value of true or false. It just doesn't compile because nil can't be compared to itself. Either for inequality or equality. So it's kind of like NaN. It neither equals itself nor not equals itself. But neither of those compile. It can appear on either side of an equality. That's weird. So why would such a weird concept exist inside Go? Like we're trying to keep things quite simple and avoid a lot of magic. Why would such a bizarre concept exist? And the answer is, it makes things simple. If you assign nil to a pointer, it won't point to anything. If you assign nil to an interface, the interface will not contain anything. If you assign nil to a slice, the slice is going to no longer contain any values. And this might seem overloaded, and this is what I mean by nil doesn't really have a type. Its type is defined by how it's used. But you can imagine if nil didn't work in these three cases, we'd have to have three unique pieces of syntax for, well, how do I stop a pointer pointing to something? How do I clear a value in an interface or something like that? What I mean by nil's type is defined by what it's being compared to is, in this case, like in all cases in Go, without exception, the types on the left-hand side and the types on the right-hand side always have to be the same. So this means that we know f is a pointer to a file, so therefore nil is a nil pointer to a file. It just took that behavior on by being in this comparison. But equally, we can say is the slice of strings s equal to nil? Again, this is known. There's no conversion, but now nil has the type of a nil slice of strings. So nil's type is defined entirely by what it's compared against. This is perhaps why it can't be compared against itself. The main reason we talk about nil is it has this unfortunate behavior with interfaces. And this is what is colloquially known as a typed nil. Here we have an example. F is a pointer to an OS file. We assign, ignore the error handling, this is part of the example. We assign an OS the result of os.open to F, and then we return it. So os.open we know returns a pointer to a file and an error. We're throwing away the error, and we're just assigning the pointer to a file to F. So all the types line up, and we return it from open. Now, this is an exaggeration to illustrate a point, but what we're doing here is, rather than checking the error value from open, we're saying if F is nil, if F is nil, then the open didn't work. If you're coming from Java, most of its strings work this way. String operations, if they can't work, they return a nil string. So it's kind of, you have to say, is the result equals nil? Well, there was a problem doing it. Now the wrinkle here is that we have a concrete type here, and we have an interface here. Now, assuming that slash missing is actually missing, so what's going to be assigned here? Nil. We're going to return nil here, but it's going to move from an os.file with a value of nil to a pointer. And I'll have to, someone chuck me a pen, just chuck me the black one over there. So we start with which we know is nil. We put it into an interface value of type. Now, interfaces are a two-word structure. They contain the type of the underlying value put in there and the actual value. So this is how type switches work. An interface knows the concrete type stored in it and the value of that concrete type. So when we assign os.file into io.writer, this type becomes pointer to os.file. We say this contains a concrete OS file and its value is nil. And this is a type nil. It has a type of os.file and a value of nil, which means it's not equal to nil, because a nil IO writer has a nil type and a nil value. And so what happens here is when we do this comparison, f equals nil is false because they're not the same. Don't forget, nil takes on the type of the thing it's being compared to. So if we return an IO writer, it's going to compare itself to an IO writer. And we can see that while the red one never works. Surprised the black one works. While these are the same, these are different. This is OS file and this is nil. And under the hood, what actually happens is these are just two words. This is each type inside a Go program is given a number. Doesn't matter what the number is, it's just an index into something. And so nil has a number and os.file has a different number. And when we do a literal memory comparison between these two words and those two words, they're not the same. And that's why nil passed through an interface does not equal nil itself. And this is the dreaded type nil problem. And so the advice, the way to fix this is never return a value containing nil. It's actually return nil itself. So let me just write that up properly. I mean, the right way to do this code is to so we can see it prints false. So in the case that the error is not equal nil, we explicitly return a nil interface. We take this nil, a nil interface, which gives us that nil for the type and the nil for the value, rather than boxing the os.file into the IO writer, which gives us an interface value which has the type of OS file and a value of nil. I can probably find a better example of this than this contrived one, but we'll do that later. So the question, yes? Yes, and this goes to the advice by, yes, the question is this still a problem if instead of returning an interface type, we return a concrete type? I've just lost the tab, and the answer is absolutely yes, there is the tab. So let's just put it back how it was. So returning false, and your thing is Yeah, because we're no longer boxing this value into an interface and then unboxing it again. And the piece of advice that backs this is it's blanking on me. I didn't reference his material directly because like those are his ideas, not mine. I don't want to claim precedence to them. Is this meme of accept interfaces return structs? So the parameters that you take in from a method or a function should be interfaces, and we'll talk about why later on. But the results you return should generally be concrete type, should be structs. There are always exceptions to that rule. For example, most of the IO package violates that. Just trying to find. Yeah. So, like we have functions like limit reader, which take a reader interface and return a reader interface. And there's probably some rule of thumb between functions do something one way, methods do that another. I can't give it. I just haven't thought enough about that to give concrete advice there. But the post you should read is by Jack Lindemann, who's he was talking about this before anybody else, which is basically accept interfaces, return structs. And if you, especially the return structs part, if you always return concrete values, you can never be in that type nil situation. I think it's one of the last things we'll have to say about nil. Just don't use nil to indicate failure. I'm sorry, did you have a question? No, it's okay. Don't use nil to indicate failure. You don't need to. Like we have multiple return values. We have the error value. You don't need to overload the return value, which was exactly the problem that you saw in that previous example. We were overloading, like open either returns a file or it returns nil to say I couldn't open the file. Like we don't need to write code like that. We have multiple return values. And this, I don't want to spend too much time on this, but I'll talk a little bit about it, which is one thing when you have programmers that come, certainly from other O languages, certainly the compiled ones, is that when they discover that you can call a method on a nil receiver, it kind of blows their minds. They get a little bit upset. They're like, how is this possible? And once they kind of understand it's possible because the receiver is just a regular parameter, they get angry because they're like, so that means every single one of my method calls, this could be nil. They get really upset because that's just not possible in Java. It's not possible in C++. The program will have exploded by that point. It's possible.
C# you can.
Okay. Yep. Okay. But you can see where the concern comes from. Something which was previously impossible. It was just not possible. Now that means that generally like for example in Java, when you call if you accidentally call a method on a nil value, it blows up at that point. Where this will blow up is it will blow up here when we try and actually access dereference B and access one of the fields. What you see is the panic will point to this line, not here, which was actually where the mistake was. We should have initialized B before we called it. Yeah, it's kind of a bit upsetting. And sometimes the inclination is, well, I need to, for every single one of my functions, I need to then wrap it in some logic. I need to say, if Bill, to make sure that B isn't nil before I call that. This is not the right way to do it. Because what are you going to do? Like that means that this whoops function now behaves. Now, if it was called incorrectly with a nil receiver, it just doesn't print anything. It doesn't blow up, doesn't leave a trace, doesn't leave a log. it just silently doesn't do anything. And that's going to be really fun to debug. The real answer is to check before you call. If something in your logic is creating these B's in an inconsistent state that they're actually nil, then you need to make that check beforehand, before you go into whoops. But for argument's sake, maybe if you have some background in preconditioned languages like Eiffel, which I don't have the book, it's on my shelf somewhere. What are some of the other things that we could do? Like, how could we could we write code that was safe in this way? Like, if I'm called on a nil value, should I panic right there? Well, given that it's going to panic 2 lines belowhand, that doesn't really add much value. I mean, a nil receiver is a programming error anyway, so whether it panics on line 2 or line 4 is doesn't really matter. What if we checked and we returned an error to say, you called me, B was nil when you called me? Is that something we can do? Yeah, and it's very Go-like. Like, we're using multiple return values, we're using preconditions before we actually do the, so it should be b.message, whatever. But this has real implications for the caller of any method. If we're saying, we're now going to put in this logic in everything that could potentially have a receiver to check that the receiver is not nil, that means every method potentially returns an error. It certainly has the signature of return error. Every method, every one. That's a lot. Every caller will have to check the error after any call. So you have, an error check after every single method call. Every interface you define would have to have an error parameter so that the implementation can report it was called on a, so that blows up from one method to the interface that describes every implementation of that. So yes, you could do that. Yes, you could use error returns to check and call out, hey, you called me on a nil receiver, but that's going to have significant impacts on your design. And the third one is to elide execution, to say if, which is the example up here, if I'm nil, then don't execute the body of the function. That's the third option, to skip the behavior that would blow up if we needed the receiver. And as I say, I think this is the worst choice, because now the operation silently does nothing. You accidentally pass nil into something, and instead of blowing up or giving a stack trace or something you can attach a debugger to, it just goes silent. It doesn't stop running, it just stops doing anything. So, faced with these choices, and thinking a lot about design by contract systems, design by contract does not seem to fit Go. There's no reasonable way to, you can check if the receiver was nil, but there's not a lot you can do with it, with that fact. You can panic, but it's going to panic anyway. You could return an error, but that's going to dramatically distort your design. Or you could skip the execution, but that's probably going to make things worse. It's going to mean you call a method and it doesn't actually do anything. So my advice is just let it crash. Because fundamentally, a nil receiver is a programming error. It's not a problem in this code. It is the thing that happened before that code. And it's usually that nil leaked in there from not checking an error beforehand. So this is why we have test coverage. This is why we have fuzz testing, to catch these edge cases that leak in through strange inputs. And I think that's where you should put your time, rather than worrying about what if this receiver's nil? What if there was an accident and the receiver's nil? I think that's a false investment of your effort. As I say, don't check for a nil receiver. Focus on your test coverage. Use your linting tools. Focus on fuzzing, because these kind of conditions don't happen in your core business logic. They happen when you're dealing with the outside world. They're happening when you're dealing with untrusted input. And tools like fuzzing are the right way to approach this. I only have one thing to say on interfaces, then we'll stop for a second. I did have a lot more things, but for some reason, once I edited it down, I only had one thing. Jason Moran, who worked, I think he still works for Datadog, had this real just kind of galaxy brain moment. He says, people have it backwards. Interfaces exist for functions that use them, not to describe the types that implement them. I'm wondering if I have the right quote there, but his point is that the reason the reason that functions exist is to describe the behavior, not for people to make impl types. Like it's that decision of because in Go interfaces are satisfied explicitly. If you have these methods, you fit through that interface. You don't have to ask and receive permission. And so interfaces in Go are this kind of key strategy we use for polymorphism. We don't have abstract types and inheritance. When we want to talk about the class of behaviors, we talk about it as an interface. It does these things. It has these methods, and anything that satisfies that interface is therefore an implementation of that. I hope this goes okay. So similar to earlier where we had that discussion of should your methods be on the pointer type or the value type, we now have this extra dimension. Is it an interface or a concrete value? So we have 4 possible states. And it's important to point out that the method set of receivers on T is disjoint to the receivers on a pointer of T. This really doesn't come up very often because behind the scenes, the compiler and the runtime take care of this a lot. Let me just get rid of all that. What I mean by show by this bad example is that T is of type T, not pointed to T. It's not this. It's a concrete value. Yet we can call a method that takes a pointer to a T, and what's actually happening behind the scenes is the compiler's actually doing this for us. So take the address of T and pass that as the receiver. Same thing. So there's a lot of magic that happens behind the scenes, just so that in Go we don't have the difference between the dot operator and the arrow operator that you have in C++, like the difference between a value and a pointer to a value. Because those are kind of collapsed, and because the compiler takes care of, this logic also works in the opposite direction. Here, T is a pointer. Oops, let me do it like that. Yeah. So what the compiler is doing here for us is it's dereferencing T to make the receiver line up. So even though T and star of T are distinct, they're actually disjoint. It's mostly hidden from us. And I say, it allows the call to operate as if the methods were available on both types. However, when a value is assigned to an interface, this illusion is broken. Let me just copy this code into... This illusion is broken. See, cannot use the T literal. As T does not implement counter, the method is on the pointer. This very long method, because the reason for this is assignment is always a copy. So it's not this T, but a copy of T that goes into this interface, and the copy of T which they take an address of, which we increment. The fix to that is that we have to actually create a pointer a pointer value to put into this interface. So, sorry, this is a very esoteric part of Go, but I wanted to close it off because it is one of the four. So say here, because everything's a copy, there's no way to wrap an interface around an existing value. A copy is always taken. So if the value is not a pointer type, then the copy of the original gets placed into the interface. And so the takeaway of this is if your type implements an interface and has methods on its pointer type, which it almost always do, then you should always use a pointer value when assigning to an interface. I would like to make sure, well, two things. One, that I have enough time left for questions, and also that we can cover the concurrency bits, because I think those are some of the most interesting ones. You can read the rest of, you can read these other points yourself. So sorry, your question is?
Yeah, it relates to the interfaces and what you just showed regarding the confusion with the pointers. It goes back to naming.
Yes.
So in our code base and so we have issues when we have a spec, and some of the fields are interfaces and some are pointers. We want to let the user know, the developer, which are interfaces, which are, because you have to assign pointers to them. So is there a naming convention that you...
That is a good question. Let's take a break and I'll think about it. My initial answer is no. Other than interfaces normally end in ER. They're those kind of, are they adverbs? They're kind of like they're doers, like readers, writers. So the question of how to let somebody know they need to give a, well, the good news is that you can't get this wrong. If you try and put a value type in there and you construct that struct with a value type, you'll get a compile error. So nothing bad, like nothing wrong can happen at runtime. It just won't compile. But in terms of better ways to hint at that, I don't know. Let me think about it for a little bit. We were talking about API design, have some stuff about package design where I spent a long time just arguing for the names of packages. You don't need me to read that yourself, to you. We step out a little bit further to package structure, which is really how to compose packages together. Some ideas about using internal packages. Something happened editing this chapter. I think the actual introduction, like this one here, project structure, it's just a bunch of random notes, so please forgive that. We won't have time to talk about error handling. You can read that. It's really a recitation of things I've been writing on my blog for a while. Just basically try to write programs that don't care too much about the actual type of the error. Just the error happened or it didn't. That's all we need to know. But what I want to finish with is perhaps the reason some of us are here, which is Go has good concurrency. So let's talk a little bit about channels and Go routines. As I opened with, some of the reasons that people adopt Go, usually performance is mixed in there somewhere. Usually people are talking about. I was talking to someone when we came in, that the reason that most projects adopt Go is they had a thing which was written in another language and it was too slow. This could be a thing about compiled languages, or it could be about just that they needed to do some parallel stuff which their previous implementation wasn't capable of. So it's important to realize that people come to Go because it has these concurrency features. So we should talk about how to use them properly. One thing I do note here is, just like this workshop, every book that you read about Go always leaves concurrency to the last section, and somehow implying that this is the most difficult thing. Like most books are structured from easy to difficult, and that's kind of strange, because we pitch Go as being a great concurrent language, but when it comes down to it, we say, I'll leave that till the end. That's a bit complicated. So we should talk about concurrency, and the properties of concurrency, channels, select, Go routine should be something that all Go programmers are really comfortable with. So that comes in two forms. The first one is channels. Channels are the way that data flows from one Go routine to another. This is the basis of Rob's don't communicate by sharing memory, share memory by communicating. I always get them round the wrong way. I'm not sure it's a really good proverb if no one can remember the ways that they go, but it's clear that when you want to move data between Go routines, you do so via channels. And channels have this property of sending data from one to another, but they also have this property of control flow, because when you send data from one Go routine to another, generally that wakes the other one up. Generally, that might put you to sleep. There may be some notion of signaling between, not just in the data, but the actual act of sending data. Closing the channel has no data, but it has a radical effect on control flow. As I said, now because a channel is necessarily shared across multiple Go routines, like it is very uncommon to create a channel and just use it yourself. It'd be a very weird kind of buffer to do that. We might ask questions about who owns the channel. Like most other resources in Go have ownership. Who owns that memory? Who opened that file? Ownership is an important problem. And ownership is important because while multiple Go routines can send and receive on a channel, only one can close it. Like everyone knows, if you close a channel that's already closed, it panics. And so that tends to complicate the design, because you need to coordinate on who's allowed to close a channel. And who is allowed to close a channel is the owner. That's the rule. So, as I say, from this we can derive some rules of channel ownership. Only the owner of the channel should close it. And perhaps we could further say only the owner of a channel may write to it. Now, you might be thinking, well, I'm using a kind of fan-in pattern where I send a bunch of Go routines out to collect data and they bring it back together. They all write to the channel. Well, in that case, the channel has more than one writer, then none of them are the owner, because without further coordination, then you will end up in a situation where there's multiple closes and you get a panic. So from this we can kind of extract, there are cases where a channel doesn't actually have an owner. And this is not necessarily the end of the world, because you do not need to close a channel to free its resources. That is, that can be a misconception. Unlike a file, which you should close if you open it, a channel is just a data structure. It can fall, once all the references of it, its memory will be freed by the garbage collector. The only property we're talking about here is this closed signal. And the closed signal is important because it's how we communicate the signaling between Go routines, not just the data. And so while we're talking about signaling, let's talk about some of the other control flow properties that channels have. Fundamentally, sending on a nil channel blocks forever. Receiving from a nil channel blocks forever. Sending on a closed channel panics, as well as closing a closed channel. And receiving from a closed channel returns the zero value immediately. And we're going to spend some time talking about these, because these are how we actually signal between Go routines. We construct control flow that extends not just in one local context, but across contexts. So, if we ran this program, we'd actually get a deadlock. If I had an example, I'd show you a little bit out of time. The reason is that this send blocks. And the reason this send blocks is because this is a nil channel. Another way of thinking about it is, you cannot send a nil channel. I think I have an explanation for it later. Similarly, receiving from a nil channel blocks. So let's think about this. Why does this happen? This is the observant behavior, but if we try to explain it from first principles, why does this happen? The first thing is that the size of a channel's buffer is not part of its type declaration. So var c_chan of string does not say how big this channel is. So it must be part of the value. If the channel is not initialized, then those bytes of memory that live somewhere for the chan of string are all going to be zeros. So that suggests that the field in the channel that says your channel size will be 0. And because this is a channel of 0 elements, it is what we call unbuffered. Now, if the channel is unbuffered, then before you can send, somebody else has to arrive to receive. This is the coordination that channels can give us in the case of the unbuffered channel. The rules for unbuffered channels are if you have a send in one go routine, that send is not complete until another go routine arrives at the point that it receives. And then effectively at that point, the value flows between them. It never goes into a kind of a send, it's sitting in some holding pattern like an Erlang mailbox, and then somebody else comes along and receives it. That would require buffering, and this is an unbuffered channel. So because the channel's nil, then the sender and the receiver have no way of finding each other. Like in this case of the nil receive, nobody has the reference to the other end of this channel. So nobody can send, so this receiver can receive. So that's why that's why it blocks forever, because there's no way to find the other end of that channel to send something into it. Now, this might seem like a lot of setup for not a lot of use, but this can be a useful property. Remember we talked before about it can be difficult to coordinate on who is allowed to close a channel. So wait many waits for both A and B to close. So we're just going around in this loop. We say, well, not A closed or not B closed, then we try and select from one of them. As soon as one of them is selectable, we then mark it as, oh, we've seen that one closed, and we go back in the loop. So eventually, both A closed and B closed are going to be true. We exit out of the loop. But this is not the right way to construct this program. Let's say that A is closed first, so this becomes ready. We set A closed equal to true. Because B closed, let me just check my logic here when I wrote this. Right. This things are slightly out of order. This comes from the third one, which is once a channel is closed, it is always selectable, which means that this doesn't just happen once. We don't just set A closed once. Come around again, and A is selectable again, is ready again. So we just stay in this loop, setting A closed to true, and never ever observe that. Now, a safe way to, as an introduction to the next thing, a safe way to do this is to nil out the channel. This doesn't, and this, so you say, well, A not equal to nil or B not equal to nil. If A suddenly becomes selectable, then we nil it out. And we just said that a nil channel is never receives. So instead of this, so this case no longer keeps firing anymore. So basically, every time one of these cases fire, we nil out the thing that fired, and so eventually we end up with none of them left. As I said. A send on a closed channel panics. We're talking about the problems with fan out. So here we have a channel of 100, we start 10 workers, they do some work sending values over to the channel, so they're fanning into the channel of C. And then when each of them has done 10 things, they close the channel. And this is a problem because eventually more than one worker is going to complete its work, they're going to try and close the channel, you'll get a panic. So the question is, why isn't there a version of close that lets us check if the channel's already closed? Like if this is such a dangerous thing, why isn't there kind of like an is closed function? And the problem is that this is a logical race. The time between checking if C is closed and then doing something with that, time passes. Somebody else might have closed it in the mid-time. It's important to realize that even though this seems like a short amount of code, the amount of time that passes relative to other Go routines can be very, very long. So you can't say things like, I just checked and then I used the value, because the state may change in between. So the difficulty is that it's not possible to write this is closed function because you couldn't use the value of it safely. Like we can write is closed by doing a select and receiving from the channel, but you can't use that value safely because there's no transaction that encompasses checking if it's closed and then using it if it is not. And generally what this boils down to is that you end up with a kind of value to check, rather than storing the using the state of the channel itself, you keep a separate closed value and you guard it with a lock. And this gives you that transaction that encompasses both checking if it's closed and closing it, and using if it's not closed. Samir has some great, Samir and Brian, I forget Brian's last name for the, have some great content on the Golang blog about pipelines, lots of this fan in, fan out stuff. And the last one is that a receive from a closed channel returns the 0 value immediately. So once the channel's been closed, you can't send a value on this channel, but you can still receive from it. Now, once the channel is closed and all the values have been drained from the channel, what is it going to, I've said that it's always ready to send you a value, but what is that value going to be? It is the default value from the channel. So that's why if we make this channel, send 3 values into it and close it, you can still read the values off that channel. Like closing doesn't throw away values that are kind of in the buffer of the channel. It just sets the marker, like a channel effectively has a buffer of values and a marker closed or open. It just sets that marker. And so if we receive 4 times from this channel, we get 1, 2, 3, and then the 0 value. And the reason that I bring this up is to talk about ranging over a channel, because if we wrote it like this, there's like some loop, or we would need some loop to tell us when we're done with the values, or worse, we would need something like to tell, did the channel give us a real value, or did it give us the 0 value because it's closed? The correct solution is to use the range idiom, which is you just range over this channel until all the values have been consumed and it is closed. And we write this, but actually under the hood, this is what the compiler produces. We've got the 2-argument form of receive, which is B and still open. If it's still open, keep going around, keep receiving values until the channel's closed. When we rewrite the form to range over the channel, we get called exactly as many times as we need until the channel is closed. So channels come in 2 forms. There's the buffered and the unbuffered form. And like all the things I've talked about today, when there's a choice, we need some kind of values or heuristic to decide, well, what should I use here? Should this channel be buffered? Should it be unbuffered? If it's buffered, what size should it be? And the suggestions that I have are ones that myself and Roger Pepe talked about a long time ago, which is basically channel sizes should in general be the 0 or 1. That is unbuffered or the buffer of 1. The buffer with 0 is for coordination, because as I said, the send cannot complete until a receiver arrives at that. That lets you write code in 2 different Go routines that you know that they've both arrived logically at the same point. The send and the receive happen, they kind of line up at that point. So you can make statements about, I've received from another Go routine, which means I know it has reached at least this point in the program. That's the coordination you can do. Buffer size of 1 is useful when you are kind of doing a piece of work in a Go routine. You want to send it back to the caller, but you do not want to block the Go routine doing that work from having to wait for the call. If you did some work, you want to send it back over a channel, that Go routine cannot finish and die until that send is finished. But it may be that the caller is not ready to receive it yet. So if you use a buffer size of 1, that gives you a place to hold that value intermediarily between the sending Go routine and the receiver. So it's a buffer between those two. As I said, deposited before it's drained. That's 0 and 1. What about all the other integers? What about 2 and 3 and 5 and 100 and things like that? And my general advice of that is, while you might be able to say, I need a buffer of 4 because I have 4 workers, or I need a buffer of 7 because I have 7 workers, or a buffer of 10 because I'm consuming 10 items. be wary for cases where people say, I want a buffer of 20,000, or I want, like 100 should be enough, or things like that. Because what they're really saying is, I don't know what the buffer size is. I just need it to be big enough. And big enough is a fairly dodgy engineering concept, which mostly works until values get really big, until you hit overload conditions, then all the channels fill up. So 0 and 1 are good values to use when you don't, they're good default values. When you come to like 4 and 9 and 31 and 1,000, just ask yourself, what's the rationale for that number? Why is it high? Like, what are the reasons that it's high? Maybe because we have 4 workers, so it needs to have 4 result slots. That's fine. But if it's 10,000 because we don't want to block something else like that, you're using it as an intermediary queue, that's problematic because, well, what if you get 10,000 entries? This queue fills up, then that queue fills up, then that queue fills up, and you have, this case where the back pressure moves back through your system. So just be wary of buffer sizes which are kind of followed by comments that say, we'll never get to 10,000 or something like that, because that's what they actually want is an infinitely sized channel. I never want this to block, and that's an entirely different question.
The only use I saw sometimes is to use a channel as a pool of objects. Very weird sizes,
Yeah, but it's always around about the engineering discussion for why is that pool that size, and it's fine to say 4 or 8 or something like that. There just has to be some indication that the author hasn't been like, I don't know how big this should be. I just want it to be so big that it never blocks. That's all you want to watch out for. There's usually a question around channels versus mutexes. Channels we talked about in the non-blocking case, or in the blocking case, it used to synchronize between go-routines. It lets you know if I receive this value that I know the sender has at least progressed to this point. Mutexes have a different role. They exist to protect a piece of shared data. So the question is always, is the who owns this data? If the answer is if the answer is go-routine A owns it and then it transmits it via a channel to go-routine B, channels are the right solution. If it is nobody owns this data, it's a counter at the package level. Nobody owns it, and so there has to be some other coordination mechanism. And that's what a mutex is for. The mutex is everyone agrees to use the mutex as the coordination structure. And to come back to, I believe it was your point. I can't remember the specifics of it, but the ownership. I want to argue that the ownership of resource belongs to a go routine. Now, when I say a resource, I mean files, buffers, the ability to write to a file, a database connection from a pool, something like that. These are resources that are finite. They need to be managed. They can't just be used infinitely. So, in the case that someone has taken a resource, has removed one from a pool, or taken a hold on one of them, they should be responsible for putting it back, or at least give that responsibility to somebody else. At all points, an owner, a resource has an owner. Someone opened that file, somebody needs to be responsible for closing it. We did an accept on incoming connection. At some point in the code, someone has to be responsible for deciding to close that connection. That's what I mean by a resource. And one of the ways that we can do this is to tie the ownership of a resource to a go routine, and then we can use tools like defer. We know, and we can therefore say, if this go routine is still running, the resource is still owned. If this go routine is exited, all the defers that close it have happened. So we tie the resource to the go routine and tie their lifetimes together. This is somewhat similar to, what is it in C++? RAII, resource acquisition. Which is a similar thing. Once we've exited from that function, something's cleaned up that memory. I'll skip this one in the interest of time. Looks like that's not very well edited either, but that's fine. So if the ownership of resources belongs to go routines, the question is now, well, we have to manage the lifetime of these Go routines. And the thing I'll talk a little bit about tomorrow, but when you start a Go routine, like you accept a connection, you start a new Go routine to say go off and do that work, you have to think at that point, when's that Go routine going to quit? Like it will usually be go some function, defer, connection.close, the rest of the business logic. So when that Go routine is finished, the defer closes the connection. You just have to answer the question of when is that Go routine going to finish? And that can be, that's entirely in your design. You can, it's usually driven by a signal like context.cancel. You can say the Go routine is going to be passed in a context, and when we cancel that context, it's going to recognize that, and that will be the thing that makes it quit. You can tie it to the underlying socket. Like if you want to make that, if you have a Go routine which is working as a worker with a network socket, if you retain a reference to that socket and you close it, then that Go routine is now going to get IOUFs and go through its close and clean up behavior. So that can be a way you can cancel that Go routine. But the thing I want to leave you on is when you see that Go statement, like geo some function, just always ask yourself, or if you see someone else write it and you're in code review, just ask the question of under what conditions is that Go routine going to stop? Because it has ownership of some resources. We want those to be freed at some point, because it's not just about if we use up the resources, we'll run out of memory. It's usually resources like files and sockets and things like that are not much more constrained than memory. So if you want to avoid leaking file descriptors, you need to keep a track of the current Go routines servicing those file descriptors. So always when you see a Go routine being started, like here's an example here. Go serve debug. When is that ever going to stop? Obviously when this serve debug function stops running, but this calls listen and serve, and we have no way of, this opens its own network socket. It won't finish serving until that acceptor is closed. We don't have a reference to that acceptor, so we can never stop this Go routine. We can never stop this Go routine. We can never free that socket. Nothing else can listen on port 8001. This is the kind of smell that I see in, so we can change them, start to do things like at least let them return the error, and start to go into things about making sure that you have some way of stopping it. So there's this stop channel which is connected to the context in some way, so it gives you ways of shutting down your application. This gets quite long, which is one of the annoying things about Go routines are so cheap and free to use, but actually to use them reliably is a lot of boilerplate which language doesn't provide, which is what I'm going to talk about in Singapore in a couple of months when I thought some more about these issues. But the simple takeaway is, every time you see a Go function, you need to ask, when is that Go routine going to exit? Because if you don't have the answer, it's probably going to run forever, and then you're probably going to run out of resources. I'm going to stop here. We have a little bit of time for questions. I can answer any of the questions here. Also, I'm not speaking till the end tomorrow, so you can come and buttonhole me all tomorrow and ask questions about what you've written in here, what you've read in here. So if we have any questions, please. Yes. The question is it possible to signal it? Yes. That's a very, very common pattern. If you read the pipelines, this is a very common pattern for shutting down workers. Now, the thing about this is closing this channel, at some point after closing this channel, they will all receive a value on CH and then exit, like they run off the end of the function, but we don't know when. And so usually this is combined I always spell this wrong, sync wait group. Actually, traditionally the waiting is done outside that, so imagine that I did that 3 times. So, and then the logic becomes close the channels to signal to the coroutines you should stop, and then wait on the wait group until they've actually done that, until they've deferred that done. And this is such a common pattern. There have been libraries in Go written for this. One is group. The OKLog project that Peter Bergon has used has got this idea of a group, which has moved. That's lovely. It's called a run group now. I'm buggered if I know where it is. Okay, it's moved to its own project. So what I recommend, OKLog run. Just remember that. This is a little framework to run goroutines in. So you specify your goroutine as a pair of functions: one that starts it, one that stops it. And the contract for the group is that when any one of these goroutines inside the group stops, for whatever reason, like probably it errors out, then the others are shut down. We have a similar concept that we wrote in Contour. With a slightly different interface. It's called a work group. And effectively you add to the group functions which take a channel, which is a shutdown channel. And the contract is, ignore that. The contract is will run all of those functions in each of their own goroutines, supplying to them their own done channel. And if any of them exits, you can imagine if you have a server that has several jobs, like it has an indexing job and a file reading job and serves several ports and some stats and things like that. If any of those goroutines enter an error, you want the whole server to shut down. So you can shut down completely, be restarted, start up again. You don't want one component of your server dying and the rest of them continuing on forever. So you want to tie all their lifetimes together. And this is what these group ideas do. So those are two. Those are two ones. There is the error group. The error group which does a similar thing. Okay, that has a wait. That is. Yeah, I was a little bit. I didn't understand. I thought that there was a way to. I thought that it would let you run functions, but it was difficult to shut them down. In fact, I think that's what it does. So there are a bunch of different, like error group, OKLog group. Those ones are all ways of tying together goroutines that need to run together as a group. And that pattern of you each get your own channel, all the channels are closed at once, and then we wait for you with a wait group is a very common thing that you can extract out into a library. Are there any other questions? Yes, at the back.
All around in the internet, you see the pattern of fanning in and fanning out channels. It looks like it adds a lot of complexity to the program. I was wondering when is the best use case?
Yeah, it does add a lot of boilerplate, and to not open the generic discussion too widely. One of the things that Rob has said, he gave a presentation in Sydney about 2 years ago where he talked about his response to the various go-to proposals. And one of the things he said is that he's not particularly interested in making your own data structures and things like that. But one of the things he recognized from the beginning of Go that it isn't really possible at the moment to write algorithms like fan in and fan out, the classic ones. You can do it for one type, but to reusable algorithms in the way that STL type algorithms work is not currently possible. And so that's the kind of thing he's the most excited about potentially that adding contracts could do, which would dry up a lot of that boilerplate, because there is no business value in reinventing. You've seen three versions of starting and stopping goroutines and wrapping them with a wait group. They're just this is not like finding a faster quick sort. There is just one answer to this, and we all just use it. But that at the moment eludes people. So I would in the document go look at that. What is it? This talk by Samir is considered to be the canonical. Brian, what's his name? Brian Mills. We're not going to play YouTube videos here. His talk from GopherCon 2 years ago about concurrency patterns is also another really good one to read about. Amazingly, we're 2 minutes early. No one has a 2-minute question? It's okay. You don't need to ask it. But yeah, I'll be around all tomorrow. If you have any questions about this material, please ask. I'm sure there are more than one typographical error in there. It's a giant document. It takes days to edit, like to go from top to bottom. So please be forgiving of the errors you find in it.